Good evening. This is a quick tutorial on calculating the ionic strength and activity coefficients for dilute aqueous solutions. So the problem we're going to solve is what is the solubility of silver chloride, a very insoluble salt, in a solution of 0.1 molar sodium nitrate. So the sodium nitrate acts as our background electrolyte because it dissociates completely, and 0.1 molar sodium nitrate will contribute 0.1 molar sodium ions and 0.1 molar nitrate ions. So the first thing we're going to do is calculate the ionic strength, and I've set up a little table here where I've got cations, +1, +2, +3. So I'll just stick in the concentration of my sodium ion, 0.1. Notice the charge on sodium is 1, and I'm computing the ionic strength, which is the sum of, it's 1/2 the sum of all ion concentrations times their charge squared. So there's the ion concentration, there's its charge, there's the concentration charge squared. And I have to do that for the anion too, so I put in 0.1. And so now there's my sodium contribution to ionic strength. There's my nitrate concentration to ionic strength. I sum them together to get 0.2, and I multiply it by 1/2. And so my ionic strength is the same as the concentration of my 1-to-1 electrolyte. And that's true if I have 1-to-2 electrolytes or 2-to-1 electrolytes, then the z² term will change the total ionic strength. But nevertheless, it is 1/2 the sum of all the ion concentrations times their charge squared. All right, so that gets me my ionic strength. Then we're going to take this ionic strength and we're going to plug it into the extended Debye-Huckel equation to calculate the activity coefficient for silver ions and chloride ions in this example. So let's go ahead and do the silver ion first. So you'd go down into the table of activity coefficients, and particularly the ion size parameter, and you find the ion you're working with. There's silver plus. Its ion size parameter is 250 picometers, excuse me. So I'm going to put in the 250 here. And it's a plus or minus 1. It's a +1 species. And let's see. The log of gamma, the log of the activity coefficient, is equal to negative 0.51 times the charge, in this case, of the silver ion. So that's going to be 1², times the ionic strength, which we computed in cell B12, times the square root of the ionic strength, all divided by 1 plus alpha, 250, square root of ionic strength, divided by 305. So this is the extended Debye-Huckel equation. It is really an empirical extension of Debye-Huckel theory, and what makes it particularly empirical are these adjustable ion size parameters, alpha. So let's see what I get. So for silver, my my activity coefficient is 0.75. So that means its activity is only 75% of its concentration. Now, if I want to do the same thing, so I'd write that number down. And I want to do the same thing for chloride, and notice the chloride ion size parameter, excuse me, is 300. So I type in the 300. And we get something that's very similar. It's now a -1 species. The ionic strength hasn't changed. Here's my activity coefficient calculation. Excuse me again. And notice I've taken the anti-log of 0.51 z², ionic strength to the square root, 1 plus B14, there it is, right there's the ion size parameter, B18 divided by 305. And the activity coefficient value for chloride is 0.753. So I'll write that number down and use those two activity coefficients to finish my solubility calculation.